you know, I am Eun Pa from the Bureau of Meteorology. And yeah, in this presentation, I'd like to talk about the impact of ozone forcing on the 2020 Antarctic supervortex event and associated surface climate conditions, which has been investigated with my colleagues Lin Zhu, Griff Young, and Irina Rudeva at the Bureau, and ACCESS-NRI at Monash University. It was Abik did this work before he joined DITMA for his current work. As you know, ozone provides an important forcing to sorry. Give me a second. Sorry about that. Southern hemisphere surface climate variability and long-term change. Due to the increase of the man-made ozone depleting substances like chlorofluorocarbons, the Antarctic ozone hole became steadily larger from the 1970s to 1990s. But we've seen the sign of reversal of that trend since 2000, together with a reduction in the emission of that ozone depleting substances. And experts are expecting the ozone hole to recover to the pre-ozone hole level in the mid-21st century. Because the Antarctic ozone depletion and increasing greenhouse gases have similar effects on the Southern Hemisphere extratropical circulations during our spring and summer seasons, Antarctic ozone recovery and increasing greenhouse gases are likely to be the two competing forcings on the southern annular mode SAM and associated surface climate in the coming decades. So understanding the atmosphere's physical processes with these two forcings has been one of the key research interests for us. Then why 2020? After the extreme stratospheric vortex weakening and warming event in 2019, the Antarctic stratosphere experienced 3 consecutive polar vortex strengthening events in the austral spring seasons of 2020 to 2022. Especially the 2020 supervortex event in late spring of October to December was the strongest on record in the last 44 years. Also, the Antarctic ozone concentration was very low in the lower stratosphere in the spring of 2020. Some studies published in the last 3 years show that the 2019 Australian bushfire smoke caused significant ozone anomalies, speculating that it could have contributed to the 2020 supervortex event. However, Solomon et al.'s recent study published in Nature actually showed that the 2019 Australian bushfire smoke didn't cause the Antarctic ozone depletion, although it made the Antarctic ozone hole somewhat larger. So although this interesting linkage between Australian bushfire smoke and the Antarctic ozone depletion seemed kind of disproved at this stage, the impact of the forcing from this significant ozone depletion on the stratospheric polar vortex and related positive SAM in 2020 was still worth exploring. Then let me first just quickly explain some basic dynamical processes associated with the spring polar vortex strengthening in general. The top plot shows the temporal evolution of zonal mean zonal wind anomalies in the upper stratosphere in relation to the spring polar vortex variations, displayed as a function of latitude and calendar months from May to December. According to this regression plot, spring polar vortex anomalies are often the result of a poleward progression of the oppositely signed westerly wind anomalies on the equatorward and poleward sides of the winter polar night jet, which ends up as one-signed anomalies over the polar cap region in spring and summer. Therefore, these latitudinal dipole anomalies of winter polar night jet provide long-lead predictability to the spring polar vortex anomalies and associated surface SEM and regional climate anomalies. Interestingly, this dynamical process was missing in 2020. So this 2020 vortex event appears to have occurred all of a sudden without any obvious precursor. And this event was poorly predicted by the Bureau's dynamical subseasonal to seasonal forecast system, ACCESS-NRI, until the beginning of October, when the vortex had gained already quite a bit of strength. One of the many possible reasons for this poor forecast performance could be that realistic ozone forcing is actually missing in ACCESS-S systems because we prescribe monthly climatological ozone forcing in our forecast systems. So in this study, we just wanted to understand what the role of the ozone anomalies of 2020 could be in the extraordinary strengthening of the polar vortex and its predictability by conducting some forecast sensitivity experiments to the climatological versus the observed ozone forcing using ACCESS-S2, which is the Bureau's current operational multi-week to seasonal forecast system. ACCESS-S2 is atmosphere, land, ocean, sea ice fully coupled dynamical sub-seasonal to seasonal forecast system initialized with high quality observed conditions. This ACCESS-S systems use JUICE for the land surface and NEMO for the ocean. And its hindcasts, like 27-member ensemble hindcasts out to 8 months lead time are available from 1981 to 2018. So that's all I'd like to say about ACCESS-S2 today, but it will be good to have another presentation just focusing on what kind of modeling experiments we can do with ACCESS-S2 available on Gaudi. So for this study, we generated one set of control forecasts forced with monthly climatological zonal mean ozone, and the other set of experimental forecasts forced with the 2020 monthly zonal mean ozone. Forecasts were initialized on the 1st of September 2020 and verified for the following September to December. And 9-member ensemble forecasts were generated for each set. And forecast anomalies were computed relative to the control hindcast climatology of 1981 to 2018 from the same system. And for the forecast verification, we used ERA 5 reanalysis data for wind, temperature, and mean sea level pressure and the Australian gridded rainfall data. So here are some results, and forecasts shown here were initialized on the 1st of September 2020, as I mentioned earlier. So first column shows the observed Antarctic polar cap temperature anomalies and the zonal mean zonal wind anomalies at 60 degrees south, displayed as a function of vertical pressure levels and calendar months from September to December of 2020. The second column shows the control forecast forced with the climatological ozone. The third column shows the experimental forecasts forced with the realistic ozone of 2020. And the last column shows the difference between these two ozone forcing runs. As I mentioned earlier, the control forecast with climatological ozone forcing couldn't predict the occurrence of the super vortex in spring 2020, as you can see here. But it kind of simulated weak westerly wind anomalies in December, together with weak cooling of the polar stratosphere from November. On the other hand, the experimental forecast with realistic ozone forcing made much better simulation of the polar cap, stratospheric polar cap temperature anomalies with more realistic temperature evolution in the low stratosphere. And it simulated much stronger vortex westerly winds in October to December. And these changes forced by the realistic ozone were statistically significant at the 90% confidence level, as indicated by the stipplings. Then let's have a quick look at the impact of the ozone anomalies of 2020 on the surface SAM. As shown in this plot, the observed stratospheric polar vortex wind anomalies reached the surface in December. So here we display the December mean sea level pressure anomalies from ERA 5 and from the control forecast and the experimental forecast initialized on the 1st of September. So these are the forecasts at 4 months lead time. As you can see, the control forecast with the climatological ozone forcing simulated the positive SAM as the observed, which implies that ozone wasn't the key forcing to promote this positive SAM event in December 2020. But the experimental forecast with the realistic ozone forcing simulated the positive SAM to be more zonally symmetric and simulated deeper low pressure anomalies over the polar cap region, which are closer to the observed than the control forecast. For our summer seasons, positive SAM tends to promote wetter than normal conditions over Southeastern Australia. And the top plot shows the observed December 2020 rainfall anomalies. Because La Nina was going on at that time, Australia was pretty wet almost everywhere except for southern Queensland and eastern Victoria and so on. But especially this wetter than normal conditions over the eastern part of Southeastern Australia was likely to be promoted by the positive SAM in December 2020. When the forecasts were initialized on the 1st of September and verified in December, the control forecast forced with the climatological ozone actually produced some kind of drier than normal conditions over many parts of Australia, which were quite different from what happened. In contrast, the experimental forecast forced with the realistic ozone produced wetter than normal conditions over many parts of Australia. And particularly, these wetter than normal conditions over Southeastern Australia with this realistic ozone forcing was quite consistent with our understanding that low Antarctic ozone could amplify the positive SAM, which could promote more rainfall over Southeastern Australia in our summer season. Finally, ACCESS-2 is currently predicting another stronger than normal vortex event in the coming spring season. So if this happens, the occurrence of the super vortices in 4 consecutive years would be truly unprecedented event in the last 60 years. And if this happens, it can promote the positive SAM in spring and summer seasons, like what happened for the last 3 years. And probably you have been following the news that seasonal forecast systems are predicting strong El Nino for the later part of this year. And the US NOAA already declared El Nino for the current conditions. And if this strong El Nino happens as predicted, it can actually act to promote the negative SAM. So if our strong El Nino and strong polar vortex forecasts are both eventualized, we can have a repeat of what happened in 2015 when a strong El Nino and stronger polar vortex had a tug of war on the SAM. So the SAM was neutral, and Australia wasn't as dry as it was expected by the strength of the El Nino. So to summarize, the 2020 supervortex event in October to December was a very unusual event in that it didn't follow the canonical mechanism of the poleward progression of the winter polar night jet anomalies, and it was poorly predicted until the beginning of October 2020 by ACCESS systems. And according to our forecast sensitivity experiments to the climatological versus the observed ozone forcings, the 2020 ozone anomalies significantly cooled the Antarctic polar cap region in the low stratosphere and strengthened the polar vortex, and therefore contributed to their predictability and amplified the vortex impact on the surface conditions, such as positive SAM and associated early summer rainfall over southeastern Australia. This really highlights the importance of ozone forcing to be improved in our S2S forecast systems. And finally, ACCESS-S2 is predicting the 4th consecutive vortex strengthening event in the coming spring. So stay tuned, not only for El Nino, but for the Antarctic polar vortex. So that's all. Thank you.
Thank you so much, Eun Pa. That was very interesting. Shoban?
So my question is does the ACCESS-S2 system currently have ozone thing in?
I can't hear anything.
These looks like these were. So did you actually? These were sensitivity experiments you ran. Does the default ACCESS-S2 system actually have the ozone detailed ozone forcing in now?
I couldn't really hear the first 2/3 of your questions. There was some kind of delay. Okay. Could you repeat your question again? Sorry.
Okay, so the earlier ones you did in October for October 2020 was with ACCESS-S1.
Yeah.
But now we're running ACCESS-S2. So yep. Does that now have the full updated ozone forcing in?
No. So ACCESS-S1 and ACCESS-S2 was basically the same system, but we fixed some errors, and one of the errors was actually reading in ozone forcing data, monthly climatological ozone data from 360 days to 365 days, which actually made the difference towards the end of the year. So that was kind of only relevant change we made in ACCESS-S systems from S1 to S2, but basically they are the same system, and ozone forcing is the same. So it's still ACCESS-S2's using the climatological ozone.
Okay, so you would need to actually get as up-to-date ozone forcing as you can from whatever sounding data. But I remember when I was working a bit with Andrew Kleckachek on this, and I haven't worked with Andrew for a while on anything to do with ozone, getting ozone data was quite difficult. I mean, we looked at mirror data and stuff like that to try and look at some runs, but in the end we never tried to do them. We tried to do them as ACCESS-1 on free, I think we were looking at, and again that would be a slightly earlier version than the GC2 version that you were looking, because it was equivalent to like GC1. But yeah, trying to put that into the code and link that into the code is still quite difficult compared to the climatological versions, because that's running still running zonally averaged versions. The more recent code that and certainly what they're doing for GC5 is a full 3D ozone type fields.
Thank you, Dietmar.
Yeah, interesting talk. So not quite sure I understood what is the forecast based on. You said there's a forecast for another event, but then previously you said the forecasts were not good. So what makes you think that this forecast is actually realistic, and what is it based on? What is causing this year event?
So you are talking about. So this forecast was made by ACCESS-NRI, which was the operational system at that time. So that was kind of the forecast available in 2020. But then we upgraded the ACCESS-S1 to S2. But as I explained, like they are basically the same system. And ACCESS-S1, this operational forecast was run on Bureau's supercomputer, but ACCESS-S2 experiments we ran were run on Gaudi. So there were just a little bit of differences, but basically they were the same. And control forecasts I showed were kind of consistent with this ACCESS-S1 forecast you see here.
Yeah, but in this case, the ACCESS forecasts are not good. They are not nowhere near what observed. So now you are saying this year they are predicting an event. And why do you think? Why would you trust it this time? And why is this event? So what is driving this? Do you have an idea of what is the driver?
Yeah. So the first part, like why I think this could be real. This could be eventualized or like verified correctly is that this 2020 forecast kind of forecast deficiency was very unusual. Like based on the hindcast of 1981 to 2018, actually we have 0.8 correlation between the forecast and the observed. So this springtime polar vortex is kind of very well predictable, at least 2 to 3 months in advance. And the reason why we have that predictability is because of this dynamical process. Like because once the winter polar night jet kind of clearly shifts equatorward or poleward with these dipole anomalies, it can actually progress towards the pole with wave main flow feedback. So many times it just ends up in one very strong anomaly in spring. That's the source of the predictability, this winter polar night jet anomalies. And that's been happening in probably autumn seasons. So the models actually simulating this dipole in winter and making that forward transition of those anomalies. That's why it's predicting. So
there's already an anomaly in the stratosphere that you suspect is coming down, okay?
Yeah, and another reason for probably the important forcing could be the ozone. Like the current Antarctic polar cap ozone anomaly is actually lowest on the record. And my colleague at the Bureau, Chris Lucas, thinks that that's probably related to the stratospheric water vapor, which was unprecedentedly high level because of the Honga-Tonga volcanic eruptions last year. So, but then because the amount of water vapor into the stratosphere, that's kind of really, unprecedented, unobserved before. So we actually don't exactly know how that will, act on the polar vortex evolution.
Thank you so much, Eun Pa. That was very interesting.